If a mass m1 and mass m2 are placed together, as I was saying in the figure, and a force F is applied on m1. Due to this force, if both the masses together move with acceleration a, then the acceleration of the system is a equal to force by mass, that is F by m1 plus m2. And between the surfaces of m1 and m2, the contact force is, at this surface, the force due to m2 on m1 as well force due to m2 on m1, both are equal and opposite according to Newton's third law. Now the contact force between m1 and m2, this is nothing but m2 into a. This is the force applied due to m1 to move m2 with acceleration a, and this is equal to m2 into F by m1 plus m2, and this is the contact force developed between the contact of these two surfaces. Suppose in the same problem, if we consider the force is applied on m2, in this case the acceleration a equal to F by m1 plus m2. Because of this force, the system will move in this direction with acceleration a. Again, at this surface, a contact force is developed due to m2 on m1 as well as due to m1 on m2, and it is written as m1 into a. This is equal to m1f divided by m1 plus m2. Now we take another model. An object of mass m is attached to a string and suspended vertically. In this case, if T is the tension developed in the string, at equilibrium, a weight is balanced by the tension, that is T equivalent to mg. The tension developed in the string is nothing but T equal to mg. What is tension? Tension is a reactional force which develops in the string. In this system, the weight of the body mg is acting vertically down. This is action. As a reaction, a force develops in the string along this direction, which is nothing but the tension developed in the string, which is a molecular interaction force. Now we consider a massless string is connected to a block of mass m and is pulled horizontally as shown in figure. To pull this mass, I applied a force F at this position. When a force F is applied at this end, automatically the reactional force tension develops in the string. This is opposite to the applied force and this is along this direction. In this case, the tension developed in the string is nothing but T equal to F, and which is nothing but m into a when the mass is moving with acceleration a. Now we take another problem. Two masses m1 and m2 are connected with a massless string and a horizontal force F is applied through the string connected to m1 in this case, and we consider when force F is applied at this end, the system is moving with acceleration a. In this part of the string, a tension T1 is developed, and in this part, the tension T2 is developed along this direction, and the resultant force acting on m2 is along this direction. At this position, T1 equal to F, and T1 is nothing but the force required to move m1 and m2 with acceleration a. We can write T1 equal to F equal to m1 plus m2 into a. Now the T2, this is the tension developed between the masses m1 and m2. T2 is nothing but the force required to move mass m2 in magnitude. That means T2 equal to m2 into a. In this case, the acceleration a equal to F by m1 plus m2. Now we take another model. Three masses m1, m2, m3 are connected with a string as shown in figure, and a force F is applied at this end. If the system is moving with acceleration a, can you write the equation for acceleration? Yes, acceleration a equal to force by mass, which is nothing but F by m1 plus m2 plus m3. When you apply a force F here, a tension T1 develops in this string, and according to Newton's third law, F and T1 are equal. At the same time, the tension T2 develops in the string between M2 and M3. This is along this direction, and the net force acting on M2 is along this direction. The magnitude of T2 is nothing but the force required to move M1 and M2 with acceleration A. In this string between M1 and M2, a tension is developed along this direction, and the force acting on M1 is along this direction. Here T3 is nothing but the force required to move M1 with acceleration A. For this problem, we can write the expressions for acceleration and tension as follows. The acceleration of the system is A equal to F by M1 plus M2 plus M3, and the tension T1 is nothing but F, and this is equal to M1 plus M2 plus M3 into A. This is nothing but the force required to move the system having the masses M1, M2 and M3 with acceleration A. And the tension between M2 and M3, this is T2. This is nothing but the force required to move the masses M2 and M1 together with acceleration A. Therefore, we can write T2 equal to M1 plus M2 into A. The tension between M1 and M2, this is T3, and this is nothing but the force required to move mass M1 with acceleration A. Therefore, T3 equal to M1 into A. These are some models related to connected bodies. While solving the problems related to connected bodies, we use a free body diagram. This is a convenient method to represent the various forces acting on the masses. In this diagram, object is taken as a particle and different forces acting on object are shown. Suppose if I consider a mass M is placed on a horizontal surface. What are the different forces acting on this body? One, it is stationary. Yes, the weight of the body, mg is acting vertically down, and according to Newton's third law, the normal reaction N is acting vertically up, and these two are equal in magnitude, and due to these two forces, because they are equal and opposite, they gets cancels, the body will not move. When a force F is applied along this direction, due to this force, the body will move. Now, the free body diagram related to this system is like this. mg is acting vertically down, N is along this direction, and F is along this direction. And these two will get cancels. And because of F, the body moves. Now we take another problem. Two masses, M1 and M2, are connected with a string. M1 is on horizontal surface, M2 is hanging over a frictionless pulley as shown in figure. Now in this case, if we consider the different forces acting on M1 and M2, the free body diagram for M1, if I consider the system is moving due to force M2G in this direction with acceleration A. At M2, M2G is acting vertically down. The tension developed along the string will be along this direction, and in this string, the same tension is used to pull the mass with acceleration A. Suppose we consider free body diagram at M1. What are the different forces acting on M1? The weight M1G acting vertically down, the normal reaction is along this direction, and the tension is along this direction. And these two are equal and opposite. These two gets cancels. Because of T, M1 moves with acceleration A. Therefore, using this diagram, we can write the equation T equal to M1 into A. Now we take the different forces acting at M2. M2G, the weight is acting vertically down. The tension is vertically up. And the system is moving down with acceleration A. What is the net force acting on the body? M2 into A. Now this is equal to M2G minus T. Why? Because M2G is in the direction of M2A and T is opposite to this. Now we take this is equation 2. solving equation 1 and 2, we get m2a, this is equal to m2g minus m1a. From this we can write the acceleration is m2g by m1 plus m2, and the tension T equal to m1 m2g by m1 plus m2. Now we take another model. Two masses m1 and m2 are connected with a string and suspended over a frictionless pulley as shown in figure. This is also called Atwood's mission. If we consider m2 is greater compared to m1, then the two masses will move like this. That is, m2 move vertically down with acceleration a, and m1 moves vertically up with acceleration a. Now we take free body diagrams at m1 and m2. At m1, m1g is vertically down, tension T is vertically up. It is moving with acceleration a in upward direction. For this we can write the equation for net force, that is m1a. This is equal to T minus m1g. Here T is in the direction of m1a and m1g is opposite to m1a. At m2, the weight m2g is acting vertically down and T is vertically up. The mass is moving down with acceleration a. Now the net force is m2a. This is equal to m2g minus T. And this is one equation and this is another equation. On solving these two equations, we can write the expressions for acceleration and tension developed in the string. On solving equation 1 and 2, we get acceleration A equal to m2 minus m1 into g by m1 plus m2, and the tension T equal to 2m1 m2 by m1 plus m2 into g. Now in this case, the tension between the rigid support and pulley, this is equal to 2T. This is along this direction. And now we take another problem. Three masses m1, m2 and m3 are arranged as shown in figure. m2 is on horizontal surface and m1 and m3 are suspended over pulleys which are frictionless, and the strings are connected to m2 as I was saying in the figure. Now in this case, if m1 is greater compared to m3, the complete system will move with acceleration a along this direction. At this position, can you write the free body diagrams for m1, m2 and m3? Okay, first we take m1. What are the different forces at m1? m1 is considered as a particle. The weight is acting vertically down, that is m1g. Let us take the tension T2 is acting vertically up and it is moving with acceleration a. Now in this case, the net force on m1 is m1 into a. This is equal to T2 minus m1g. Now at m2, if we consider the tension in the string is T1, the tension in the string is T2. T1 is acting along this direction and T2 is acting along this direction. mg is vertically down and the normal reaction is vertically up. These two will get cancelled and the mass will move because of T1 and T2. For this we can write m2 into a equal to T1 minus T2. We take this as equation 2. Now similarly at m3, if we take this as T1, the tension at this position also T1, this is the same string and it is moving down with acceleration a. m3g is acting vertically down, T1 is vertically up. Hence we can write m3 into a equal to m3g minus T1. This is equation 1, this is equation 2 and this is equation 3. On solving these three equations 1, 2 and 3, we can write the expressions for acceleration a, tension T1 between the masses m2 and m3 and tension T2 between the masses m2 and m1. Now we take another problem. Two masses M1 and M2 are connected with a string and are suspended over a frictionless pulley on an inclined plane of inclination theta, as we are seeing in the figure. And due to the force M2G, the system is moving in this direction with acceleration a. When it is possible, if this M2G is greater compared to the force along this direction on M1, then it is possible. Now in this case, if we consider T is the tension developed in the string, the tension is along this direction at this position and along this direction at this position. Now we try to draw a free body diagram at M1. This is an inclined plane. M1G is acting vertically down. This can be divided into two components. One is M1G cos theta, another is M1G sin theta. This M1G cos theta is normal to the surface, and opposite to this, the normal reaction is developed, and M1G sin theta, this is parallel to the surface, and this is nothing but the force which slides down, which pulls the body down, and opposite to this we are having the tension, and these two will get cancelled. As a resultant of T and M1G sin theta, the body will move along this direction with acceleration a. For this we can write the equation. The net force acting on M1 is M1 into a. Since it is moving along this direction, T is positive because T and a are in the same direction. We can write M1 into a equal to T minus M1G sin theta. Now at this position, that is at M2, the free body diagram, M2G is vertically down, the tension T is vertically up, and it is moving down with acceleration a. The net force on M2 is M2 into a. This is equal to M2G minus T. Using these two equations, we can write the expressions for acceleration and tension. On solving these two equations, we can write M1 plus M2 into a. This is equal to M2G minus M1G sin theta, or a equal to M2G minus M1G sin theta by M1 plus M2. This is the expression for acceleration. Now substituting acceleration in expression T equal to M2G minus M2A, we get the tension developed in the string. Tension T equal to M1 M2G into 1 plus sin theta by M1 plus M2.